Welcome back to another Explainer, where we take complex engineering reports and, well, break them down into strategies you can actually use. Today, we're looking at the Farley Stormwater Management Strategy. But, we aren't just talking about pipes and puddles here. We are talking about return on investment. How do you design infrastructure that protects the environment while aggressively optimizing literally every single dollar spent? Okay, let's dive into this. So here is the core problem of modern urban engineering. On one hand, you've got incredibly high environmental goals, right? We need clean water, protected ecosystems, flood safety, the whole shebang. On the other hand, you have realistic civic budgets. You can't just throw unlimited funds at a development project. So how do you bridge that gap? How do you ensure that the money invested in managing stormwater yields the absolute highest possible return for both water quality and community safety? Well, it turns out the Farley project offers a pretty fascinating blueprint on exactly how to do this. Here's our roadmap for today. First, the Stormwater ROI Challenge. Second, the Treatment Train Strategy. Third, proving returns with music. Fourth, smart sizing for massive savings. And finally, the ultimate environmental payoff. Starting off with Section 1, the Stormwater ROI Challenge. To really appreciate this approach, we kind of have to look at the historical challenge. For a long time, civil engineering had a very specific and, honestly, a very expensive way of dealing with stormwater. Basically, just dig a massive hole at the lowest point of a development. The whole idea was to just catch everything in one giant detention basin. But the Farley Investigation Area, they throw this old-school playbook right out the window. They realize that relying on just one massive basin to do all the heavy lifting is financially inefficient and, frankly, environmentally inadequate. It's just a terrible ROI, and we really have to move beyond it. That brings us to Section 2, the Treatment Train Strategy. Now, what's really interesting here is how they answer the question, what is the alternative to that giant, expensive hole in the ground? It's called a treatment train, which is an integrated water cycle management approach. So instead of one big basin, it combines multiple systems in a series to manage both the quantity and the quality of the water. Think of it less like a massive storage bucket and way more like a highly efficient environmental assembly line, where each individual station does a specific job perfectly, optimizing the total system. So here is how that assembly line actually operates across the landscape, broken down into 3 primary steps. Step 1 is vegetated swales. These utilize the natural topography and dedicated riparian corridors to slow down overland flow and filter out coarse sediments before water even reaches the main basins. And the absolute best part, nature does this for free. Step 2 relies on gross pollutant traps. These are underground mechanical units placed at the end of street pipes to catch large litter and debris. Finally, Step 3 brings the water into sedimentation ponds to drop out all those fine sediments and nutrients. Let's zoom in on that final step for a second, the primary sedimentation ponds, specifically looking at the massive 16,500 cubic meter southern basin. The real brilliance here is the dual design. It's a hybrid basin. It has a permanent wet pool that slows the water down so fine sediments and bound nutrients, things like phosphorus and nitrogen, drop out of suspension. But right above that, there is an extended detention zone that temporarily holds back peak storm volumes, so it tackles pollution filtering and flood prevention simultaneously. You're getting 2 vital functions out of one piece of infrastructure. That is exactly how you maximize your ROI. Let's move to Section 3, proving returns with music. But how do you actually know this interconnected assembly line will work before you go and spend millions of dollars building it? Well, you have to prove it using rigorous simulation software called music. And the number 20 is absolutely vital here. The engineers didn't just run a quick little test. They ran continuous climate simulations over a massive 20-year timeline. And they didn't use generic data either. They used highly localized 6-minute interval rainfall data from the nearby Maitland weather station. They literally stress-tested this system against prolonged dry spells and intense wet seasons to mathematically guarantee that return on investment over 2 full decades. To ensure absolute accuracy, they mapped out the exact terrain. They separated the pervious areas, where water can naturally soak into the soil, from the hard, impervious concrete, where it just runs right off. Each type was assigned strict pollutant generation concentrations based on standard industry guidelines for residential urban catchments. So by modeling the exact pollutant export of the area, the engineers knew exactly what their treatment train had to handle. No guesswork. So the crucial point here is time. Following the journey of the water, when a storm hits at hour 0, water enters that extended detention depth, which is usually 0.3 to 0.5 meters above the permanent pool. But it's intentionally designed with a slow release mechanism of 24 to 48 hours. Why? because this slow release ensures the water stays in contact with the vegetation long enough for biological uptake to occur. The plants literally absorb the nutrients right out of the water before it's released downstream. It's pretty amazing.
On to Section 4, smart sizing, massive savings.
Now let's talk about the actual financials, specifically looking at those underground gross pollutant traps we mentioned earlier. There's a huge temptation in engineering to size these for a massive 100-year storm, but doing so is prohibitively expensive and, honestly, highly inefficient. Instead, the Farley strategy explicitly sizes them to capture the peak discharge of a 3-month average recurrence interval storm, essentially the standard frequent rainstorms we see a few times a season. Because that frequent rain washes off the vast majority of the street pollution, sizing it for these smaller storms captures maximum debris at a fraction of the cost. It's just a brilliant financial decision. But wait, I know what you're thinking. What happens when a 10-year or 100-year storm actually does hit? If the trap is only sized for a 3-month storm, won't it just overflow or explode? Well, the engineering specification solves this by dictating that the pits must include an internal bypass weir. For any storm larger than the 3-month capacity, the extreme floodwaters safely bypass the filtering mechanism entirely. This ensures the captured trash doesn't just get washed back out, and it prevents upstream street flooding. So you get maximum pollution capture on a strict budget with zero flood risk during extreme weather. Finally, Section 5, the ultimate environmental payoff. We've seen the smart design, the rigorous modeling, and the cost-saving optimizations. So what is the ultimate ROI? Well, look at these final metrics. By using this multi-layered train instead of a single giant hole in the ground, total suspended solids drop by over 80%. Total phosphorus plummets by 45 to 65%, and total nitrogen is reduced by a proven 45%. The system doesn't just meet environmental targets, it completely exceeds them. Which leaves us with this core takeaway. Smart stormwater management isn't about building bigger, it's about building smarter. The Farley strategy proves that by integrating natural systems with smartly sized mechanical units, you can achieve world-class environmental protection while maximizing absolutely every civic dollar spent. So I'll leave you with this question. Take a look at the infrastructure projects happening in your own community right now. Are they just brute forcing it and building bigger, or are they utilizing these ROI principles to actually build smarter? Think about it. Thanks for joining me on this explainer today, and I'll catch you on the next one.